Today we shall discuss about polymerization techniques. Now, so far we have learned about mechanisms of polymerizations, whereby we have seen how monomers can be converted into polymers using condensation polymerization mechanism or addition polymerization mechanism, whereby we have seen we can use free radical route. We can use ionic route, cationic, anionic, and apart from that, we have seen coordination polymerizations where some metal catalysts can be used, and the polymerization proceeded via coordination technique. So, coordination mechanisms. So, such mechanisms are available for polymerization of different types of monomers. Now, for condensation, we have monomers which have specific functional groups to react within themselves and condense. They produce byproducts, so that is one way. And for other cases, we had the vinyl monomers, that is, they contain unsaturation, and uh, other mechanisms were capable of polymerizing such monomers, vinyl monomers. Now, even after knowing these mechanisms by which the monomers can be converted into polymers, but if you are given with monomer and other ingredients, you will not be able to polymerize them until the polymerization techniques are known to you. What kind of techniques can be utilized for the formation of these polymers? So that is important to know, and unless you know this, you will not be able to polymerize. So this is our discussion of today, that polymerization techniques, and today we shall discuss four basic techniques. Although apart from this we have many sub techniques available, but we will discuss four main techniques or basic techniques that are being used for polymerizations, and these techniques are mainly for free radical polymerizations, because when we were discussing the mechanisms, we mentioned that free radical polymerization is the easiest and mostly adopted polymerizations commercially or industrially, or even in the laboratory, because of the ease of the process. So that way, the techniques that we will be discussing today are mostly applicable for the free radical polymerizations, and for that we have four basic techniques available. One is the bulk polymerization technique. Next one is the solution polymerization technique. Third one is the suspension polymerization technique. And fourth one is the emulsion polymerization technique. So these are the four basic techniques which can polymerize the vinyl monomers in FRP mechanism, that is free radical polymerization mechanism. Now let us first see what is the bulk polymerization technique. Now in bulk polymerization technique, the system is composed of only two components. One is the monomer that you want to polymerize, and the initiator. Now you can have more than one monomer, because you can also go for free radical based copolymerization. So that monomer or monomers that you can take, and you can take the initiator. So these are the two components which constitutes this bulk or mass polymerization technique. Now this polymerization technique, we generally carry out this polymerization in this bulk mode for high conversion. We aim for high conversion, but actually we encounter a lot of problems in it if we want to go for high conversion, and that I will mention. And it is mostly applicable for free radical kinetics that already being mentioned. And we have many common monomers which are being polymerized using this bulk polymerization technique, like ethylene, styrene, methyl methacrylate, that is for the formation of polyethylene, polystyrene, polymethyl methacrylate. Mostly the homo polymers are being uh, made using a bulk polymerization technique. Although I have mentioned that you can co-polymerize, but examples of co-polymerization using bulk technique is not much available due to several other problems. But it can be done. That is the thing. So that is, this bulk polymerization technique can be used for co-polymerization, but because of the several disadvantages we have in this technique. Generally, some homopolymerization using some special or additional, modification of this technique, we can polymerize these monomers in this bulk polymerization mode, and we avoid the copolymerization generally. But it can be done. Now, the advantage of this technique is that you can obtain most pure product. That is, purest form of the polymer can be obtained using this bulk polymerization technique, because you are only using monomer and initiator, and we know that initiator is used to the extent of say 0.5 to 1% with respect to the monomer. So you can just ignore the amount of initiator present along with the monomer in the system, and that way at the end, at the end product, you are only having the polymer with ignorable percentage of initiator. So that way, what we call it, that the bulk polymerization produces the purest form of the polymer. So you can get the most pure polymer using this bulk polymerization technique. But along with it has so many disadvantages that I was mentioning, and because of this we hardly use this technique for copolymerization on commercial scale. And the first disadvantage is that the GL effect or the Tromsdorf effect that we have discussed during free radical polymerization, whereby the free radical polymerization can enter into the runaway mode beyond 40 to 50% conversion because of tremendous rise in viscosity of the medium. As monomers are converted into polymer, there will be more densification of the system, and that way the viscosity would rise. And once you have the rise in viscosity, the diffusion of the larger or matured grown radicals coming close to each other and thereby getting terminated either by combination or disproportionation technique, that becomes difficult, because as the viscosity of the medium is increased, the rate of diffusion also goes down, and that way the diffusion of the giant polymer radicals which are about to terminate, their diffusion rate falls at a faster rate as compared to the monomers. So that way the rate of termination sharply decreases, whereas the rate of propagation in a effect of that increases, because that rate of propagation would require, or propagation reaction would require uh, one giant radical coming close to a monomer. So that way the monomer, because of its lower mass, as its diffusion is not much affected because of the rise in viscosity of the medium, so that monomer can easily diffuse towards the growing radical, whereas two mature radical ready for termination, they cannot diffuse faster too close to each other. So that way the rate of termination falls, whereas the rate of propagation increases. So that actually drags the reaction into the runaway mode, whereby there is a tremendous rise in propagation without termination, and we have gigantic molecules being formed which are not terminated, and that way the reaction readily forms gel, insoluble mass. So that what we call it as a gel effect, that is the main drawback of a bulk polymerization system, because you have no measure being provided in the system to control the viscosity. Now in order to cut short this process, that is prohibiting the reaction to enter into the runaway mode, as a system cannot do that intrinsically, so we need to add some agent extrinsically, so that we can resist the system from moving into that runaway mode, and for that the chain transfer agent or CTA being added. And chain transfer agent, we have already seen it actually, with the high transfer constant, it actually resists the propagation and it induces termination, and that way we can control the molecular weight and also prohibit the reaction from entering into the runaway mode. But that way we are actually terminating the reaction, means we are cutting short the molecular weight. So that way, using of this chain transfer agent, although it prohibits the reaction from entering into that gel mode or runaway mode, but at the same time it cut shorts the molecular weight, and that way the maybe that highest range of molecular weight that could have been achieved is actually achieved in only smaller fraction and not as a whole for the polymer. So that way, use of a chain transfer agent can further widens the molecular weight, whereby the chain transfer agent stopping the polymerizations which has started later, uh, which are growing at that point, say after 1.5 hour or 2 hour of the reaction, whereby we have some 40 to 50% conversion. So at that stage, whatever growing chains are there, so use of a chain transfer agent actually terminates them. Whereas in the initial phase, we had the fully grown polymers. So at the initial phase, maybe you have very high molecular weight polymers, and when the chain transfer agent is used after 1.5 hours or around 2 hours to resist the reaction to move into the runaway mode, so thereby whatever chains were growing at that time, they were being stopped. So that way we have a much wider distribution of the polymers when we use a chain transfer agent in bulk polymerization technique to prohibit the reaction from entering into the runaway mode. So that is, you can understand that whatever limitations being created there in the bulk polymerization technique because of this. Now, the rate of propagation increases very fast, as I mentioned, because of this runaway mode, and also the your this kinetic chain length nu, that also increases because you do not have the termination, and that way the broadening of the molecular weight distribution in natural course, if no chain transfer agent is added, that also results in a bulk polymerization technique. Third point is that viscosity increases as conversion increases, making heat removal and processing of the polymer more difficult. Now, why it is being said that the heat removal becomes difficult? Because we know that this free radical polymerizations, these are highly exothermic, and that exothermicity basically controls or drives the polymerization, and because of that heat production during polymerization, uh, and also the polymers which is being formed in general, they are being insulated of heat and electricity, so they will not naturally dissipate the heat, rather they will accumulate the heat within the polymeric mass. And because of the growth of viscosity, the stirring also uh, does not remain too effective to dissipate the heat. So that way, lot of heat being stored or accumulated within the polymeric mass, and that would create lot of side reactions in the polymer as well. Some local gel formation, some local heating effect and local charring effect, creating hot spots, means those local charring points. So that would actually make the quality of the polymer inferior. So this is another disadvantage, that is the quality of the polymer. Apart from being much wider in molecular weight distribution, the otherwise the quality of the polymer sometimes not remain very good or effective for the post application. And also that way, if some gel formations, local cross linking, local charring, these sort of things happen, so that actually make the polymer processing more difficult and more energy consuming. Now, because of these disadvantages, the polymerization in bulk mode, that is being carried out in stage-wise mode, whereby initial 10 to 25% conversion of the monomer is carried out in a big tank through stirring. And in that monomer conversion range, we can see the viscosity growth is not too high. That way the stirring is good and effective, so heat dissipation is also good. And also not such problems that we discussed, or disadvantages that we discussed, that all these would creep in at this conversion range. So up to 25% or sometimes 30% conversion can be done in a reactor under stirring mode. And after that, it can be I mean your uh, it can be transferred in a mold kind of stuff, and the slabs or films can be prepared there after further polymerization. So rest of the polymerizations can be done in the mold kind of stuffs, in the form of slabs or films, because that 25% converted monomer and 75% unconverted monomer, that mixture is now poured into that a mold kind of stuff, whereby the further polymerizations can be carried out. Now, as this mass is sprayed within the mold, having much higher surface area, uh, here the heat dissipation becomes little bit improved, because of the lower thickness of the mass, and as the higher surface area. So that way, in stage 2, in the form of this slab or film, the polymerization can be rest of the polymerizations can be carried out. Or otherwise, it can also be done after that initial 10 to 15% conversion. The overall that mass can be taken into a loop reactor, whereby under the motion the polymerization can be carried out. So that way, the heat dissipation and growth of viscosity does not interfere with further conversion of the monomer. And this is the technique being adopted for the polymerization of polyethylene, polypropylene, this kind of polymers, whereby this bulk polymerization technique is preferred, although it is not exactly the free radical polymerization mechanism being utilized for polymerization of your polyethylene or polypropylene. Rather, that coordinate catalysts are being used. But the technique adopted is that your catalyst and the monomer, and initial after that initial 10 to 15% conversion, it is then taken into the loop reactor, whereby the further polymerization is carried out under motion or under a flow of that mass. So that way, the difficulties or limitations of the bulk polymerizations being tried to overcome, and that way your the purest form of the polymer, which is the biggest advantage of this technique, that is being tried to achieve. Now, after this bulk polymerization, we can have another technique which is called your solution polymerization, whereby the components are here monomer initiator, and one additional one is a solvent. Now, we can have a throughout homogeneous solution polymerization technique or a heterogeneous solution polymerization technique. The differences are between this is that the solvent that is being used in the system, if it is a solvent for both monomer and the polymer which is being formed, then the system remains homogeneous, and there would be no phase separation. So these are the point of differences in a homogeneous polymerization solution polymerization technique, whereby in the beginning the system is homogeneous because the monomer is soluble in the solvent so as the initiator, and with time the polymer which is being formed, that also remains solubilized in the solvent. So from beginning till end, the system remains homogeneous. So that way it is called a homogeneous solution polymerization technique. And the polymerization of vinyl acetate, acrylonitrile, esters of acrylic acid. For these kind of monomers, we can adopt the, overall homogeneous solution polymerization technique. Now, in heterogeneous polymerization technique, we have the monomer being soluble in the solvent, but the polymer which is being formed with time, that does not remain soluble in the solvent. So, with time, we can observe precipitation of the polymer. So, what we see that homogeneity in the beginning and precipitation with time. So, that way the phase homogenization followed by phase heterogenization. So because of this, we call it as a heterogeneous solution polymerization. So in the beginning, we have a homogeneous system, but with time, we see there is a precipitation of the polymer because the polymer is not soluble in the solvent that is being used. So that way it is called heterogeneous solution polymerization system. And in this case, the precipitation of the polymer is obtained in the form of powder or granules depending on their size. Now, acrylonitrile polymerization in water or vinyl chloride polymerization in bulk, right? In bulk means vinyl chloride, when you polymerize the polyvinyl chloride which is being formed, that will precipitate out. So that way there will be a phase separation, and it is then equivalent to that heterogeneous solution polymerization technique. Now, in both the cases, that is whether it is homogeneous polymerization or heterogeneous polymerization, we see that the free radical kinetics is aptly applicable for both. Now, because of the use of solvent, we have several advantages as compared to the bulk polymerization technique. First of all, the solvent acts as a diluent and aids in removal of heat of polymerization, because that was another one of the major concern of bulk polymerization, that is the heat dissipation. And because of the use of solvent which acts as a diluent in the system, so that actually aids in the removal of heat dissipation of the polymerization reaction. Now, use of solvent reduces viscosity, and overall polymerization process becomes much easier because of the lowering of the viscosity, the starring effects and all these things becomes much easier because of the presence of the solvent. And of course, use of the solvent gives you better thermal control of the reaction, which was not present in the bulk. right? So that way the thermal control over the reaction becomes much easier uh, in the solution polymerization technique. Now we have some major drawbacks of this technique as well. First of all is the intrinsic chain transfer reaction which can be induced by the solvent. Now almost all the solvents has the capability of inducing the chain transfer reaction. Some has the higher capability and some has the lower capability. Now you have to be very careful while selecting the solvent in a solution polymerization technique, and you need to check what is the transfer constant of the solvent. If the transfer constant is much higher in for the solvent that is being used, then you will finally see that almost no polymers are being formed. So that is a major concern for the solution polymerization technique, is that the chain transfer reaction to solvent molecules. So you have to be careful that you must use a solvent which has minimum or much lower transfer constant. So that needs to be checked. Otherwise, it would lead to a much lower molecular weights or such type of molecular weight which is not useful in the later stage. So that is the major concern, the intrinsic transfer reaction. So that can interplay during the propagation. Now, use of solvent can create a lot of environmental hazards, environmental pollution due to the release of solvent vapor, and you cannot control that, right? Means there always be some solvent vapor in the plant, in that and surrounding, and you cannot resist that, you cannot control that. So that would again create a lot of environmental hazards, even fire hazards, particularly in the your winter season, where you have much lower moisture content in the air. So during that time there could be disaster in terms of catching fire and all. Lot of such hazards are associated with the bulk use of the solvent in solution polymerization. And when the polymer is formed after polymerization, the solvent that you recover, you need to recycle it. So you must have that provision, number one. Number two, the polymer which is being isolated, it would also contain some solvents, so that traces of solvents content in the polymer needs to be removed. So that will again release the solvent vapor in the atmosphere. So that way, the plant, in the plant area, you must have this solvent vapor collector, and that collector will collect most of the solvent vapor, or maximum possible extent, to the maximum possible extent, the solvent vapor, and then condense it and will reuse it. So that way the recycling operation, recovery operation, so these should be should be very good in the plant for adopting this technique, whereby you can reduce the waste of the costly solvent, and also you can restrict the your environmental problem to some extent in the plant area. So these are the major disadvantages of solution polymerization, although it is advantageous than bulk in terms of controlling the reaction, uh, controlling the process. But you can see a lot of intrinsic and extrinsic problems are there, and for that you have to have some your additional measures when you want to go for solution polymerization technique. Now, the third polymerization technique you can adopt for free radical mechanism is the suspension or bead or pearl polymerization technique that we see here. And suspension, that it is a heterogeneous system, means where you have the monomers with the help of inorganic suspension stabilizers they are suspended in the dispersion medium, and that way the components of the suspension polymerization techniques are the monomer, inorganic stabilizer, and these are basically the suspending agent that would aid the suspension of the monomer in the dispersion medium. And in most of the cases the dispersion medium used is water, and the initiator should be oil soluble, that is it should be insoluble in water and should be soluble in organic solvent, and the monomer also should be insoluble in water, and that way it can be suspended with the help of this inorganic stabilizer. Most of the cases clay is used as inorganic stabilizer because clay remains suspended in water, and in that mode it can also help the monomer to get suspended in water. And the initiator that is being used is of course monomer soluble, or what we call it as a oil soluble initiator, or soluble in organic solvent and should be insoluble in water. Now here you see that the system is heterogeneous, and you have the water insoluble monomers and water insoluble initiators. They are being suspended with the help of a suspending agent uh, in water, right? So this is the normal suspension polymerization system. Now if you can compare with your bulk, it was a homogeneous system. In solution, it was also a homogeneous system. Maybe in the later stage, because of the precipitation or insolubility of the polymer might settle down and become heterogeneous. But to begin with, that is a homogeneous system. But the suspension polymerization, from the beginning itself, it is a heterogeneous system. And here you see we have the suspended I mean these are the monomers suspended over or adsorbed over the suspending agent, and overall this remains suspended in the dispersion medium or water, and that way the monomer droplet size remains within 0.001 to 1 centimeter in diameter. And here you see the initiator, as it is oil soluble or it is monomer soluble, then naturally it will not remain in the water phase, rather it will diffuse inside the monomer droplets, and on application of the temperature it will initiate the polymerization in these monomer droplets. So that way you can imagine that each of these monomer droplets, they act as individual bulk system, just like the bulk polymerization system where you have only monomer and initiator. So these monomer droplets, they actually act as individual bulk polymerization system because you are using water insoluble initiator, and they will of course, because of the compatibility and solubility in the monomer, they will diffuse inside the monomer droplets, and on application of the temperature they will start or initiate the polymerization in each droplet. So each monomer droplet acts as a mini bulk polymerization system. So you can say that a suspension polymerization is actually a combination of many mini bulk polymerization system with much better control, because you have water as a dispersion medium. The medium is heterogeneous itself, so that way the chances of growth of viscosity because of polymerization in original bulk mode or bulk technique is also not present. So that way you can control the reaction in terms of heat dissipation or heat removal in a much better way. So that way bulk polymerization technique means it's a miniature form of the bulk polymerization technique, and that way we also call the suspension polymerization as the mini bulk polymerization technique. Now once this polymerization is over, what we can see that the your polymers they will be more dense, so that way they will try to settle down once the monomers are converted into polymer because of the densification of this suspended particles. So that way we can have precipitation in the form of bead or pearl of these polymers in the suspension technique, and hence the technique is also referred as bead or pearl polymerization technique. And this kind of suspension polymerization technique can be adopted for polymerization of styrene, methyl methacrylate, vinyl chloride, vinyl acetate in such type of monomers. Now, the advantages that we can have in this suspension polymerization is that the system has a low viscosity due to the suspension status. Heat removal is much easier in the process because number one, the viscosity is not getting increased, and number two, you are using water as a suspending agent, and we know that water as a liquid has the highest heat capacity, means it can absorb lot of heat with little rise in its own temperature. So that way water can absorb lot of heat of polymerization intrinsically. So the removal of the heat is much improved in this case, and polymerization yields finely divided stable latexes in case you can resist the precipitation after polymerization. So for that you need to viscosify your water such that the heavier polymers which are being formed, they should not get precipitated. So in that case, apart from your this monomer, inorganic stabilizer, oil soluble initiator, water, we need to add some viscosifier. Viscosifier means that component which can increase the viscosity of water, and once the viscosity of water is increased, then you can resist the precipitation after polymerization. uh, and the polymer will remain suspended as well in the medium, which you can refer or call it as a polymer latex. So in the latex form, if you have any applications such as your in coating application or in paints or as adhesives, where the polymer latex dispersed polymer that is used directly, so for that you can avoid the precipitation, and you can directly use the, I mean, post polymerization product, the suspended polymer or polymer latex for this application. So you can have that advantage as well, that the product which you are getting in the form suspended form, you can use it for these applications. Now, there can be some disadvantage in spite of so many advantages. Some disadvantage can be there in this technique, this suspension polymerization technique, and these are the polymerization. This polymerization technique cannot be used for polymers whose glass transition temperature is less than the polymerization temperature. This is very important point to consider, that the monomers which will be polymerized, the polymer that you will be getting or which will be formed in this technique, the glass transition temperature of that polymer uh, should not be less than the polymerization temperature. Otherwise you will get the aggregation of the polymer instead of getting precipitation in the form of bead or pearl. You will get a lump or aggregate because the polymerization temperature is higher than the glass transition temperature of the polymer. And once you get the polymer precipitated, in case you have not viscosified your medium, so in that case you must have a proper technique for separation and purification, because you have used a suspending agent and that will be entrapped within the polymer. So that way you must have a very good separation technique and purification technique, so that you can remove the suspending agent from the polymer uh, for its application.